So here's presenting Introduction to Dynamic Programming. I would now like Utkarsh, our mentor, our speaker for this particular session, to come over and go ahead with the session forward. So about Utkarsh, he has worked as a DSA problem setter, as well as he has worked as a mentor at our platform, and he is well versed with Java, DSA, and React.js. All right, so here you go, Utkarsh. You can now take it over with the session ahead.
Is it audible? Shravani, is it audible? Is it audible? So am I audible? Okay, because you're not audible to me. So yeah, so I'll be sharing my screen right now, and we're going to start off with understanding what dynamic programming is. But for a moment, let me start my video on. So yeah, is it okay? Yeah. So let me share my screen first, and we have the PPT over here, right? So we are going to be looking at what essentially a dynamic programming paradigm is. So, so basically, how many of you are well versed with what recursion is? So basically, recursion itself is a concept where we call a function again and again. So there is one function, it calls itself, then that function again calls itself, and so on. So whenever a function is called, right, it gets loaded onto the top of the call stack, right? And whenever the function call is executed, the function gets wiped out from the call stack. So a popular example could be if you are printing your name inside a function, right? And you are recursively calling that function. So your name will be printed onto the console. Then the recursion call will happen. Again, your name will be printed onto the console. Again, the recursion call will take place. Again, your name will be printed onto the console. And this process will happen forever until you provide a base case to stop recursion from taking place. So a base case is a way using which you can essentially backtrack out of the call stack. So that is what recursion is. In a nutshell, it is function calling itself again and again. And behind the scene, what happens whenever function is called, the function address is loaded onto the top of the call stack, right? And whenever the function call is completed, the function gets wiped out of the call stack. So now, why basically why I am telling you about recursion in dynamic programming? Because recursion is the heart of dynamic programming. You cannot understand dynamic programming without having been well versed with recursion, right? So dynamic programming is essentially an optimization technique over recursion. Let me make this very clear. Dynamic programming is not a data structure. A lot of people get confused. It's not a data structure. It's basically a optimization technique over recursion. You can also call it a type of algorithm, right? It's not a data structure at all. Even though you use data structure in the process to basically optimize the problem, right? Altogether, it's an algorithm, not a data structure. So let me now open the let me now open the VS Code. So I hope all of you use some kind of an IDE, right? So a lot of you may be coming from Java background, C++ or Python, but the core concepts that we're going to talk about in this particular webinar is going to be constant for all programming language, right? So this is the folder that I have in my laptop. I basically opened that using VS Code. Now I'll be basically writing a code for Fibonacci numbers, because that is the very primitive kind of example, typical example which everybody learns whenever somebody starts off with dynamic programming. So we are gonna make a file over here, say Fibo, and I'll be writing in Java But as I go on, I'll be telling you the parallel for what you'll be doing as in Python or C++. So here I have the file. Uh, yep. Let me make the class first. Okay, but before moving on, let me first give you an overview what a Fibonacci number is. So how many of you are familiar with Fibonacci numbers? Can you raise your hands? What Fibonacci numbers are? Uh, I think it is being taught in class 12th in maths. Okay, so let me state that. So Fibonacci number is basically a type of sequence, right? A sequence of a number that follow a particular type of fashion, right? So whenever you have to write a sequence, you should know from where to start, right? You should know the starting terms of the sequence, right? So in this case, the starting term here is 0 and 1. So basically, we start off by assuming that the zeroth Fibonacci is 0 and the first Fibonacci is 1, right? Now, how do we generate the next terms of the sequence? So basically, that is given by the sum of previous two terms, right? So if the zeroth Fibonacci is 0, first Fibonacci is 1, then what's going to be the second Fibonacci, right? It's going to be the sum of previous two Fibonaccis. So that is going to be equal to 0 plus 1. That is 1, right? Now, how do you generate the next term? That is equal to the sum of previous two terms. 1 plus 1, that is 2, right? Now, how do you generate the next term? That is going to be equal to the sum of previous two terms, that is 1 and 2. So 1 plus 2 is 3, right? The next term is going to be 5, next is going to be 8, next is going to be 13, and so on, right? So let me reiterate this once. What we did, essentially, to write a sequence, we should know from where are we going to start, right? We should know the starting point to write the sequence. And by default, the zeroth Fibonacci is 0. Yeah, yeah, sorry. So by default, the zeroth Fibonacci is 0, right? And the first Fibonacci is 1. And I told you how do you generate the next terms of the sequence. That is by adding the previous two terms. So likewise, I generated the next terms of the sequence like this, right? So basically, the general formula to write nth Fibonacci is t n is equal to t n minus 1 plus t n minus 2. I hope this is clear. So if somebody is having any doubt in this, you can raise your hands and probably you can unmute yourself and ask me. I'm looking at your charts. Right? Okay, so I think nobody's having any doubt. Okay, so let us move on. So this is the concept of Fibonacci numbers. Now we have to write a code that basically tells the nth Fibonacci number. You have to write a code that basically tells the nth Fibonacci number. So how 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 you're going to be doing this? So basically, if like somebody's having any idea, you can probably unmute yourself or raise your hands or write it in chat. Okay. So basically, we are going to be doing this using recursion, right? So I'll be coming to that later, but for now, let me make the class first. So we are writing this, we are basically in the fibo.java file, right? So the class name and file name in Java should be same. So I'm writing public class fibo, right? So basically the file name and class name are same. And over here, let me make the uh, main function as well. Main method, public static void main string array args. Basically, this is the main method. Like in all programming language, I think except Python. In C++ also there is a main method, but I think in Python, you guys don't have any main. But anyways, let us come over here and write the method that basically generates the nth Fibonacci number. I hope the problem statement itself is clear. We are writing a code that tells me the nth Fibonacci number. If suppose I pass 7 in the method, that is going to be returning the 7th Fibonacci number. If I pass 10 in the method, that is going to be returning the 10th Fibonacci number. Okay, let me make the method first. Public static. What should be the return type of this method? So Fibonacci number, we have to return the Fibonacci number, right? The nth Fibonacci number, which is an integer. So the return type here should be int. I hope this much basic is clear, right? So public static int, the name of the method. Let me write fibo underscore recursion. Okay. And over here, I'm going to be taking in the signature of the function the value of n, right? So basically, I'll be calling this function from main method, right? By passing a n to it. Suppose n is 5, right? And I expect this particular function that whenever I call this function from main method, this particular function from this particular main method, this function is going to return the value of 5th Fibonacci number, right? So for the time being, consider this method as a black box. It knows how to return the nth Fibonacci number whenever you pass n from the main method, right? It just knows how to do it. No brainstorming over that. It knows, so it knows, right? Now, how are we gonna write the logic to do it, right? So basically, we are gonna be taking the help of recursion. Recursion is gonna come in and aid our process to find the nth Fibonacci number, right? So basically what I say, so basically this is the common formulation to find the nth Fibonacci number. Tn is equal to Tn minus 1 plus Tn minus 2. The nth Fibonacci number is equal to the sum of previous two Fibonacci numbers, right? So that is what we discussed here, right? So uh, basically what I'll be doing, so basically this function knows how to give the nth Fibonacci number, right? So if I call this function recursively, by passing n minus 1 to it. This knows how to give n minus 1th Fibonacci number. So basically, we are looking at the problem from the high level point of view. We are not deep diving right now. We're just making our assumptions. That let me comment this. Let me remove this for once. This method knows how to return the nth Fibonacci number, right? Fibo underscore recursion n knows how to return the nth Fibonacci number. So if this function knows how to return the nth Fibonacci number, this will know how to return the n minus 1th Fibonacci number, because essentially these two functions are same. And if this function knows how to return the nth Fibonacci number, this would know how to return the n minus 1th Fibonacci number, right? So this is my faith from recursion. This is my faith from recursion. So a lot of times, just a little bit, just a little backdrop to the problem. A lot of times, what we do, we try to solve the problem by keeping faith on recursion, right? We first generate our assumption. We first generate our faith from this function, right? Uh, this method that it knows how to do something. What it knows how to return the nth Fibonacci number. This I'm talking about this method. It knows how to return the nth Fibonacci number. And if I recursively call the function by passing smaller input, which is n minus 1, n minus 1 is naturally smaller than n. If I pass smaller input, it knows how to do that job as well. So this is going to return the n minus 1th Fibonacci number. That is my faith from recursion. So this t(n-1) term is being taken care by recursion. So let me catch that value in a variable, say factor 1, f1, or let us name it t(n-1), t(n-1). Okay, say f1 because you cannot put space between n and 1. So say f1. So this is my factor 1, right? Now what is going to be my factor 2? If I again recursively call this particular function by passing n-2, so this is gonna be my factor 2. Let me mark the indentations properly. Okay, okay. So this is my factor 2. So this was the faith number 1 from recursion. That recursion will return the n-1th Fibonacci, and this is my faith, again a second faith from recursion, that recursion will return the n-2th Fibonacci. Okay, so this is my faith 2. Okay, at this point, I want to give you a chance to ask your doubts if there is any. Just raise your hand and Shavini will give you the rights to unmute yourself and you can ask in the microphone. Yeah. Or you can probably write in chats as well. At this point, I want to give you a chance to ask your doubts if there is any.
Guys,
Just
please
raise your hand and
ask
Shavini
doubts.
will give you the
Yeah.
rights to unmute yourself and you can ask in the microphone. Okay. I think, okay, so I think there is no doubt as of now. So I cannot see any hand raised. So I think I should move on. Okay, now you know your factor 1. Your factor 1 is parallel to t(n-1). Okay, I think there is something in chat. Okay, so this is factor 2 that is parallel to t(n-2), right? So your recursion gives factor 1 which is parallel to t(n-1), and your recursion gives you factor 2, f2, which is parallel to t(n-2), right? Now, how do you, so this was your phase from recursion, right? That recursion will solve the smaller subproblems. Recursion solves the Fibonacci for n-1 and recursion solves the Fibonacci for n-2. But if you look at the problem from the high level, your problem was to solve for Fibonacci of n, right? Which still remains unsolved. So your faith is at one side and your expectation is at one side. So how essentially are you going to be bridging that gap between your faith and expectation? Your nth Fibonacci is essentially equal to n-1th Fibonacci and n-2th Fibonacci. So your nth Fibonacci, or say answer, here answer is your nth Fibonacci, is equal to factor 1 plus factor 2. Okay, and this is your faith uh, bridging idea. Okay, faith bridging idea. Okay, now you have calculated your answer, right? So you return your answer from this particular function. Okay, so I hope this this much of recursion is clear. I mean, I don't want to deep dive into the recursion tree as of now, but just by looking at the problem from high level, by keeping faith on recursion, how do you bridge the gap between your faith and your bigger problem that you essentially started with to solve, right? So this is the code to print the nth Fibonacci number, right? But there is one thing that is missing over here. So anybody who would like to point out what's missing in this particular code, you can write in chats. whenever you write a recursive code, you always have to stop the recursion from taking place infinite number of calls. So that has got two implications. It stops, it doesn't, you know, uh, completely fill the stack, recursion stack. Second, it helps you build your answer because whatever is returned from the recursion stack is given to the is given back to whatever is present in the recursion stack, so that you uh, keep on building your answer down to the stack. So, but for now, let us keep it simple. Whenever you write a recursive code, you always incorporate you know a base case, right? So your base case here is the assumption that we started off with, that zeroth Fibonacci is 0 and the first Fibonacci is 1, right? So here, let me put the base case that your zeroth Fibonacci is 0. So we are returning 0, and your first Fibonacci, right? The first Fibonacci is 1, right? So this is the base case. So if I have to, you know, deep dive the code, uh, this happens to be the base case, the first two lines, right? The next two lines happen to be the faith keeping part, where you keep faith on recursion. That recursion knows how to do the job. It will do it. Whatsoever will happen, recursion knows how to handle its job properly. It will calculate the n minus 1th Fibonacci and n minus 2th Fibonacci, and it is gonna store those two values in f1 and f2 respectively, right? Now, how do you kept your faith, and you had your bigger problem to solve. You know, you had your assumption to start off with, right? The bigger problem was to calculate the nth Fibonacci, right? So you're gonna basically gonna be adding these two factors together to generate your nth Fibonacci, right? And finally, you're gonna be returning your answer from this method, right? So this was your recursion code. If I run this is gonna be okay. Let me print it also. Let me, for the time being, move it to left. Let me write the print statement to print the result. Okay, so your fifth Fibonacci is 5, right? So let us see it over here. Zeroth, this is zeroth Fibonacci. First, second, third, fourth, and fifth, which is 5. So your recursion has done your job, right? This faith method works. It has done the job, right? Now, you know, this was about recursion, right? And I told you that recursion is optimization. Dynamic programming is optimization over recursion, right? So at this moment, let me, since my writing tab is not working properly, so I wanted to show the image of this recursion tree to you. Let me explain the recursion tree over here. Okay, you started off with finding out Fibonacci of n, right? And inside the function, you are basically making two recursion calls by passing n minus 1 and n minus 2. So just look at the tip of this recursion tree. This is Fibonacci of n, and this particular guy is making two recursion calls. So these two branches that are being branching off from the tip of the tree, they basically depict the recursion call that are taking places. That's taking place, right? So this is Fibonacci of n minus 1. This is Fibonacci of n minus 2. And assume yourself to be Fibonacci of n minus 1, right? Again, that guy is gonna make two recursion calls by sending two smaller inputs. So if this is n minus 1, this is first going to make the first recursion call to n minus 1 minus 1. which is Fibonacci of n minus 2. And this guy is going to make the second call to n minus 1 minus 2, which is Fibonacci of n minus 3, right? And similarly, this Fibonacci of n made the second recursion call to Fibonacci of n minus 2. Now this Fibonacci of n minus 2 is again going to make two recursion calls. So this, if this is n minus 2, this is going to make it to n minus 2 minus 1, which is n minus 3, and this is going to make it to n minus 2 minus 2, which is n minus 4, right? And this particular process is going to take place. This particular tree is going to branch off like this as we go down the level, right? So now let us put some values in the tree. Let me show you some better image. Yeah, this is fine. So if, let me search across this better image. Yeah. So let us just put some values to n. So if this was Fibonacci of 5, right? This Fibonacci of 5 is going to make two recursion calls. First to Fibonacci of 5 minus 1, which is 4, which is over here, right? And second to 5 minus 2, which is Fibonacci of 3, because that is how you are writing the calls in the function, right? If you are n, you're making recursion call to n minus 1, the first recursion call, and the second recursion call to n minus 2, right? So using the same parallel, if you are 5, you are making the first recursion call to 5 minus 1, that is the first recursion call. So here is 5 minus 1, which is 4, Fibonacci of 4. And if you're 5, you're making the second recursion call to 5 minus 2, which is 3, which is Fibonacci of 3, right? Now assume yourself to be Fibonacci of 4. If you're Fibonacci of 4, you are also going to be making two recursion calls. First to Fibonacci of 4 minus 1, which is Fibonacci of 3, and second to Fibonacci of 4 minus 2, which is Fibonacci of 2. And each of these functions are going to be making two recursion calls, and therefore this whole branch is going to branch off as we go down the level, right? And as you remember, we put up a base case that Fibonacci of 0 is 0, Fibonacci of 1 is 1. And I told you there exist two implications of writing a base case. First, it doesn't let you to get caught in a uh, uh, infinite function call, right? Because these guys will keep on calling each other if we do not put a base case. What do I mean by this? If this is Fibonacci of 1, this will make a call to Fibonacci of 0 from the first call. And from the second call, this is going to be making the second call to Fibonacci of 1 minus 2, that is minus 1, right? And this minus 1 is again going to be making two recursion calls, and we are going to be going down the level, and we are going to go until negative infinity. Negative infinity means we are making infinite number of recursion calls. So that was the first implication of writing a base case. The second implication is that it helps you build your answer to the bottom of the stack, because Fibonacci of 1 returns 1, right? If you remember in the code, let me show the code also once to you. Fibonacci of 0, when n is equal to 0, we return 0. When n equals to 1, we return 1, right? So here your n equals to 1, right? Here your n equals to 0. So this guy is going to return 1 to Fibonacci of 2, and this guy is going to return 0 to Fibonacci of 2. And what Fibonacci of 2 is going to do, it's going to hold these two values in f1 and f2. In f1 we basically have 1, and f2 we basically have 0. And this Fibonacci of 2 is going to add them up together, and it's going to return it to Fibonacci of 3. So Fibonacci of 2 returns 1 to Fibonacci of 3. And since this is also a base case Fibonacci of 1, this is going to return 1 to Fibonacci of 3. So if you are Fibonacci of 3, in factor 1 of Fibonacci of 3, you are getting 1, and in factor 2 of Fibonacci of 3, you are getting 1. So this Fibonacci of 3 is going to add them up together, and it's going to return it to Fibonacci of 4. So likewise, your recursion is going to take place. So each of these functions is going to compute its value, and it's going to return it to its parent, right? And its parent is again getting values from left and right. It's getting added together, and it's going to return it to its parent, right? Similarly, Fibonacci of 4 is going to return the answer to Fibonacci of 5. Fibonacci of 3 is also going to return the answer to Fibonacci of 5. So in Fibonacci of, if you're Fibonacci of 5, you're getting the value stored in factor 1. If you're Fibonacci of 5, you're getting it stored in factor 2. And Fibonacci of 5 is going to add them up together ultimately, and it's going to return it to the main method, because that is where we were calling this Fibonacci of 5 from, right? So yeah, you're passing 5 over here, right? So this was the, one second, let me put my laptop in charge. Yep. So this was the recursion tree, right? So the recursion tree has got one major problem, right? Let me show that problem to you. If you look at it over here, over here, we are calculating Fibonacci of 2 over here. And again, we are calculating Fibonacci of 2 over here, right? That is useless computation. If I have calculated Fibonacci of 2 once, then why I am calculating it again, right? That is one problem with recursion, right? That there exist overlapping sub problems. I hope you're able to identify what the overlapping sub problem is. Over here, I am calculating Fibonacci of 2. Just look at it over here. Over here, I am calculating Fibonacci of 2, and once again over here, I am calculating Fibonacci of 2. Another subproblem that exists over here is I'm calculating Fibonacci of 3 over here, and again I'm calculating Fibonacci of 3 over here. So right now, just understand that in recursion, there exist overlapping subproblems that expenses the time computation power, right? We do not need to do these useless computations once again, if at all we have calculated it beforehand. So at this point, if you have any doubt regarding whatever all like I've covered, just put that in chat or raise your hand or unmute yourself. I mean, until now we talked about recursion. I gave you Fibonacci example to make you understand what recursion is. We looked at what faith is in recursion. How do we keep faith? And faith gives us answer for smaller sub problems, right? Next, we talked about how do you build your faith? How do you bridge your faith till your expectation? You start off keeping a bigger problem in your head, then you have to bridge that with the faith that you kept with recursion, right? Next, we talked about base case. We talked about two implications of base case. First, it prevents you from making unlimited calls. Second, it helps you build the answer down the recursion tree, right? Because over here, if Fibonacci of 1 and Fibonacci of 2 was not the base case, had they not been the base case, we would not have built the answer for Fibonacci of 3, Fibonacci of 4, Fibonacci of 5, right? They help in building the answer, right? And the last thing that we talked is that in recursion, there exist overlapping subproblems. There exist problems which we have already solved before, which need not be solved again, right? Okay, so at this point, if I talk about what is the time complexity for this particular code, right? How much time does this particular code takes to run, right? So if you're not familiar with time complexity, it is basically a reference frame, right? It is basically a reference frame that we use to tell whether the computation is rather expensive or it's fairly cheap. That is what time complexity is, simple terms. How much time does a code take to run, right? So one simple way to calculate the time complexity of a tree problem or recursion problem is just look at the tip of the tree. The tip of the tree is fib of 5, right? From the tip of the tree, how many calls are getting diverged? So basically, there are two calls that are getting diverged, right? So keep two, keep two at one place, right? Then raise 2 to the power of the height of this recursion tree. So this height of this recursion tree is n, right? If n is 5, the height is 5, right? Because from 5 we went to 4, from 4 we went to 3, 3 to 1, 2 to 1, right? From 5 to 4, 4 to 3, 3 to 2, 2 to 1, right? If this was n, from n to n minus 1, n minus 1 to n minus 2, n minus 2 to n minus 3 until 1. So the height of this recursion tree is n. If the height is, if n is over here, n is 5, the height is 5, n is 7, height is 7, n is n, height is n, right? And the number of calls that are getting branched off from the base is 2. 2 calls are getting branched off because we are making 2 calls. So the time complexity for this particular code is going to be 2 raised to the power height of the tree, which is n, right? Which is n. So over here, your n is 5. So this particular expression evaluates to 2 raised to the power 5, right? But in general, we won't be passing n, we will be passing, we won't be passing 5, we'll be passing n. Be passing the values like this. Int n is equal to 5, and then we are going to be passing 5 here like this as n, stored in n. Therefore, the time complexity is 2 raised to the power n. Now, little bit about the graph of 2 raised to the power n. If at all you're coming from a little bit of maths background, 2 raised to the power n is basically an exponential function, right? With even small increments of x-axis, the values that are there in y-axis change exponentially, right? So this is a expensive computation. That is all I want you to know for now. Recursion is an expensive computation, right? Because it is taking exponential time to handle this particular task. Now we looked at there exist some overlapping subproblems, right? There exists some overlapping subproblems over here. Fibonacci of 2 is occurring twice, right? If we are calculating Fibonacci of 2 once, then why are we calculating it over here as well? Similarly, if Fibonacci of 3 is over here, then why are we calculating this Fibonacci of 3? If kind of we are able to solve this particular issue, then we will be able to reduce the time complexity from exponential to linear. And obviously, you know, the graph of linear is like this. It's not expensive at all, right? So this is where your dynamic programming comes in handy. So at this point, let me show you the slide. Okay. I think there's okay, let us okay, there is some kind of a hang in my laptop. So okay, so first let me write it over here as well. First we looked at recursion. How do we solve a problem using recursion, right? Okay, now we saw that in recursion there exist overlapping subproblems, which makes okay, yeah, which makes the time complexity exponential. And this implies this is expensive. Recursion is expensive, right? But there exist overlapping subproblems in the recursion tree that we just saw. So do we have the ability to essentially leverage that overlapping subproblems and reduce the time complexity from exponential to linear? So that is where dynamic programming kicks in. Let me write it down over here. It helps to solve overlapping subproblems. Okay. Now, how are we going to solve the overlapping subproblem, right? So there exist basically two steps to do that. First is to define a storage. Let me first give you the basic idea what we are going to do, and then we can write the code. So the basic idea here is to, if suppose we are calculating Fibonacci of 2, right? Fibonacci of 2 is going to be 0, 1, 1. Fibonacci of 2 is going to be 1, right? So this Fibonacci of 2 is going to return 1 to Fibonacci of 4 in factor 2. In F2, we are going to get 1 from this Fibonacci of 2, right? So if we try to store that particular value in some kind of a storage, right? And when we come to this overlapping subproblem, then instead of recomputing it, let us fetch that stored value from the storage and not recompute it once again, right? Let me reiterate this. While we solve for Fibonacci of 2, Fibonacci of 2 is 1. So this guy is going to return 1 to Fibonacci of 4. And that one is going to store in factor 2 for Fibonacci of 4, right? While we once again come to calculate Fibonacci of 2, I want to store that particular value beforehand. Over here, while I calculate it, I want to store it beforehand in some kind of data structure, some kind of memory location, right? So that when I once again come over here to recalculate it, I'm able to fetch that from memory and I can avoid these recursion calls. Okay, at this point, once again, if you have any doubt, confusion, you can write in chats or raise your hand or you can unmute yourself. Okay, I think we should, okay, there is some pop-up. Okay. Okay, so I hope the basic idea how do we optimize the problem is clear. While we return, we store that, and whenever we encounter the same overlapping subproblem again in some kind of branch of the recursion tree, we are now going to do the expense of making the recursion call once again. We are going to fetch the stored value from the storage. The storage may be an array, a hash map, a vector, you know, any storing data structure, right? Over here at this point, let me give you a hint. How do we decide the storage? Storage could be anything, right? It could be a matrix, a array. So focus on the number of parameters that are varying in the recursion call, right? Just one parameter is varying, that is n. So if number of parameters that are varying is 1, so the storage will be of one dimension. If the number of parameter here varying is 2, the storage is going to be of two dimension, right? So here the number of parameter that is varying is 1 because only n is varying. N is varying, n was initially n, then it went to n minus 1, n minus 2. So just n is varying, just one variable is varying. So your step number 1 is to define storage. From define means what is the dimension of the storage. Here it's going to be 1D. So as you know, 1D storage could be array, a list, right? So over here I'll be keeping a array, right? Your next step is to define the meaning to that storage, right? So I say that So this 1D array, I'm calling it DP. So this is a DP array, right? I'll be calling the 1D array as DP. Your second step is that you define the meaning to each index. So your DP of n is equal to value of nth Fibonacci number. Uh, I think somebody's mic is switched on. Okay, yeah. Okay. So your step one was to understand the dimension. Can you guys mute your audio? Voice?
எங்க போறீங்க?
Yeah, thank you. So your step one was to define the meaning. Your step one was to define the storage based upon looking at the number of parameters that are varying. Just one parameter is varying, so your storage is going to be 1D. The second step is to define the meaning to each and every index of the storage. So here I say that dp of n at the nth index of the dp array, we are going to be putting the nth Fibonacci number, right? So let me just demonstrate it once. Your dp of 0 is going to be containing the 0th Fibonacci number, which is 0. Your dp of 1 is going to be containing the first Fibonacci number. So what is the first Fibonacci number? That is 1, right? So let me put 1 over here. The dp of 2 is going to be containing the second Fibonacci number, which is 1. And your dp of n is going to be containing the nth Fibonacci number, right? It's going to be containing the nth Fibonacci number. So your two steps are ready. Your storage is decided and the meaning to that storage is decided. So let us optimize this recursion problem and lower the time complexity. All right. So you don't need to do anything. Just there involves a two-step process that you need to keep in head. So first, let me copy this same function, the recursive function. Fine, I just copied it. So let me write it down. This was recursion. This is memoization. Just a little bit of jargon. This method is called memoization, right? Whatever we just discussed, that we're going to be keeping an array, right, defining meaning, storage to it, that whole entire process is called memoization, right? Just a fancy term, nothing more than that. Okay, so there exists a two-step process using which you memoize the recursion. First, while you're returning, you do not return it like this. You first store the value in the storage, then you return. So we discussed the meaning. dp of n will have answer. Okay, let me pass the dp array as well in the signature. Over here, after we calculate the answer, we have to return. Okay, at this point, I know this particular statement is going to be confusing you. So let me again show the picture to you. Your task was to calculate Fibonacci of 2, right? Fibonacci of 2 is stored in answer, right? Fibonacci of 2 is calculated and it's stored in answer and you're returning it to its parent, which is Fibonacci of 4, right? So if that is stored in answer, before returning, we are going to be storing it storing it in some kind of data structure which is called a DP array at the nth index, right? And before making these two recursion calls, I'm going to be checking if my DP of n is not equal to 0. That means I have already pre-calculated that value and I have stored that in the storage. So there is no need to make these two recursion calls once again. So from here, I want to return DP of n. So these are the two steps that involve in optimizing the problem from recursion to memorization. Step 1, decide your storage. From decision making of storage, I mean that decide what dimension your storage is going to be of, be it 1D or 2D, just by looking at the number of parameters that are varying in the recursion, right? The second thing is define meaning to the storage. Over here, I said that DP of n will contain the value of nth Fibonacci. And just to elaborate that statement, I wrote this DP of 0 will contain the value of 0th Fibonacci, and 0th Fibonacci is 0. DP of 1 will contain the value of first Fibonacci, which is 1. DP of 2 will contain the value of second Fibonacci, which is 1, right? And DP of n is going to contain the value of nth Fibonacci, which is which you have to calculate. So just let me once again take you to this particular diagram. Just understand this at a high level, right? So basically, let me first explain that you in code, and then we'll be moving to this diagram. So here what is happening, here what is happening, we are calculating the answer, which is the value of Fibonacci of n, and before returning, right, we're returning it at line number 46, but before returning that, we are storing it at DP of n, right? Before returning, you have to store. That is point number 1. So just to elaborate this particular statement, let me take it once again. Let me take you once again to the this diagram. So while we are returning for Fibonacci of 2, we have stored the value of Fibonacci of 2 at the second index of DP array. At DP of 2, we have stored the value of Fibonacci of 2, right? And once I once again come at this particular branch, I won't be making the recursion call, because at DP of 2, my value for Fibonacci of 2 is already stored. So I'll be just fetching that value and I'll be returning, right? I won't be making the recursion calls. Just take a look at it over here. We are returning before making the two recursion calls, if we have already pre-calculated that value before. And how do I know it? Because at all places in the array, zeros are stored by default. And if there exists a non-zero number, now that means we would have already calculated that value beforehand. So this is how we are going to be saving the recursion calls. I hope this is clear. Okay, so let me write the time complexity for this. So any guesses for the time complexity? Do you want to unmute yourself and write it and tell the time complexity for this particular solution? Initially, we were getting the exponential time complexity, right? Yeah, I think, uh, yeah, I think you have unmuted yourself. Okay, yeah. So this is gonna be of linear time complexity. Let me show it to you how. So basically, using memoization, you save this particular call. You are not making call to this function, and you're not making call to this function as well, because Fibonacci of 3 is already calculated. So this is basically not a two branched call now, right? This is not a two branched call now. There exists only one branch, because in this particular branch you're not going. In this particular branch you're not going, right? So we can say that this time complexity is equal to linear time, right? It is equal to order of n, which is linear. So this is order of n, right? So we looked at what recursion is, what problems does recursion have, right? We looked at what base cases are. We looked at what is the time complexity of a recursion solution, right? Then we looked at what dynamic programming is, how does it solve the problems that we had in recursion of overlapping subproblems, and the technique we developed to basically conquer that problem is by keeping a storage, right? And before returning from the function, storing that value, and before making the two recursion calls, you are fetching that value and then you're returning, right? So there exists another type of optimization that is called tabulation, right? So in that, you basically do not make recursion calls. You basically keep a 1D data storage and then you fill that using a for loop, right? But since we are out of time, I think we won't be doing that right now. But in the next sessions that we'll be taking, I think we can cover that in that. So if you have any doubt regarding this, whatever has been covered, you can unmute yourself or write in chats, and then I'll be happy to take up your doubts. So if you have any
Thank
doubt
you so much,
regarding
Utkarsh, for your
this,
valuable
whatever has
insights
been
on
covered, you can
dynamic
unmute yourself
programming.
or write
Guys,
in
please go
chats,
ahead
and
and
then I'll
ask
be happy to
if you have any questions or any
take
queries
your
regarding the
doubts.
same. Please go ahead and ask him. Please use the chat box to reply if you don't have
So
any
if
doubts to reply if you don't have
so
any
if
doubt. I see no questions in the chat box, so I believe everyone is clear with the concept which has been shared in the session by Utkarsh. So I thank you, Utkarsh, for sharing your valuable insights with us. All right, guys, go ahead and quickly fill the form. For those who haven't yet filled the form, please go ahead and fill the form. And meanwhile, I'll just share my screen and show you how the website looks like, so that you can get a idea and insight about how we have a. All right, I hope every one of you has filled the form. So yeah, quickly go to the Play Store and you can download SkillVertex app. Over there, you can just check. You can just download the app and sign in.